Hello everyone, my name is Joon Kim and I'm out here to talk about linear regression. So before we dive right into the concept and how do we apply this to our real world, let's consider this case. You're the statistician in the school and you're trying to see or measure the distribution of height and weight of the students. So the best method at here to use will be a scatter plot. So there could be various combination of weight and height. For example, there could be a person who have a height of 182 centimeters and weight of 71 kilograms. And there could be 166 and 57 kilograms and on and on. So I made a sample data for 20 people for 20 height and 20 weight paired together and made a scatter plot based on this. And as you can see, there is some kind of positive correlations between them. What does it mean? What does it mean to be the data to have a positive correlation? It says, it means as the data of one or as the value of one category goes up, the dependent variable goes up also. So there is a positive correlation. So in the plot, you can see that as the height goes up, weight goes up. Then we now need the distribution of the data. But how can we predict the other person of some kind of height? And by using that, how can we find the weight of that person? So as an example, how can we find the weight of the person with height of 182 centimeters? What if it is 63 or 97 or 54? But we can see that this is some kind of like a function relationship. As we get one height, then we get one weight value as a prediction. And what is the most simple function we know? What is the most simple type of function? It is linear function. And linear function looks like y equals mx plus b, where x is our independent variable and y is our dependent variable. So in this case, we can say the weight is equal to some kind of slope m times the height plus b, some kind of constant. So let's make some function and draw on the scatter plot. So here's a scatter plot we saw at the previous slide. And let's say, just assume any constants. Let's say the function is weight equals to slope of 1.025 times height minus 100. Then the plot of that function looks like this, the red line at the middle. Okay, so this seems to be kind of reasonable since it is dividing in the middle. It is dividing the two data in the middle. And the distance between the lines and each data point looks quite reasonable, looks quite balanced, right? So how can we find then the optimized model or optimized function to predict this? To find that optimized model, we need to know the concept of residual. Residual is the difference between actual data, so actual y value, and subtracting the predicted value by our model from there. As you can see on the plot at the right, you can see there's a black dashed line for each point, and that is connected to our line model. However, this is not a best indicator for our model, since let's think about there is a residual which has a negative value of 100, and there's a 10 points which are residual of plus 10. That seems to be balanced and numerically, but actually in the real world it is not. So we actually use the MSE, which is the mean squared error value. So mean squared error in mathematically, it is the sum of residuals squared divided by number of the data plus. So as you can see, in the right side, there's a squares in the plus, right? Squared for each points in the data. We add up the area of all squares and then divide it by the number of data. And in this case, it is 20. And which have a minimum mean squared error value. The model which produces minimum mean squared error value is the most optimized model. So as you can see, like this looks complicated, but this is just same with the previous slide, MSE. But we changed our actual value to yi and the predicted value as a like mx plus b format. So the function L is the loss function or MSE function, and we're calculating the mean squared error of the model. But how? So how do we find the optimized model, or how do we find which model produces the mean squared, which model produces the minimum mean squared error data value, sorry. The algorithm we use at here is called gradient descent. So gradient descent and our loss function, as you can see it here, our loss function will look like some kind of polynomial function with a x squared. And this is how it'll gonna look like. And you can say there's a absolute minimum at the middle of our plot, and that is our goal. That is where we want to go, since it has a minimum value for our loss. Okay, then let's say we're at this point. Then we want to go to this minimum point. So we're gonna gradually move to there, slowly, step by step. But how do we do that? How do we move our loss towards the minimum point? At here, we use the concept of derivative. So look at this 2 points. We're moving from the before one, previous one, to next one. We're finding the direction of the movement by using derivatives and multiply that value by some kind of dx, which we call as a test rate, and here represented with the Greek letter gamma. Okay, so we do this multiple times until we reach the absolute minimum of the loss function. Okay, so this is how we do gradient descent. Don't worry, you don't need to do it like by your hand, but it is good to know, right? So basically, we get our theta 1 and theta null for our previous constant or initial constant of our prediction model. And we're gonna subtract dx times the derivative of the loss function to get a new value for theta null and theta 1, which is represented as a theta null hat and theta 1 hat here. Then by combining this, our new prediction model will be y equals, weight equals to theta null hat times weight plus theta 1 hat. Okay, so let's see what happens after doing this gradient descent algorithm. So this was our previous model or initial model, which had weight equals 1.025 times height minus 100. So our theta null was the constant, so 1.025, and our theta 1 was equal to y-intercept, which is negative 100. And the loss, the mean squared error, which was the sum of all areas of the squares and then divided by the number of data points, is equal to 73.1797 at here. So let's see what changes are made after applying the gradient descent algorithm to this model. So after gradient descent, there's some kind of changes in there. So our theta null has from 1.025, it increased to 1.0683, and our y-intercept, the plus b, has changed it from negative 100 to negative 107, 0.9844. And you can see that our loss got reduced, right? But not that dramatically. So why? Why loss is too big at here? We can see some reasons for this. We can list some reasons. So first, there's too small size of data. We use 20 data points, but think about if it is like 100 or 1000. Then the model or the gradient descent algorithm will be easier to like produce the minimum loss and make a better prediction model. That's why we say more data is better for statistics. And another reason for this big amount of loss is the model itself. So we are using linear regression model here, but there's a thing called much advanced version, for example, like polynomial regression model or logistics regression model. Those are more advanced techniques which can produce a better or more accurate result. But as you know, we're not gonna do this by hand. We're not gonna do a like derivative every time we do this. So this is mostly done by the computer by using code. So for doing this, for explanation, we're gonna use the scikit-learn, which is Python library for machine learning. Okay. Okay, so we're gonna move to here. So this is using Google Collaboratory, and if you didn't check this out, this is a really good like online platform for Jupyter like notebook. So you can use this freely. It is open source. Okay, and let's go back to our linear regression. So we're gonna use these libraries, these Python libraries. First, NumPy for generating arrays, vector, and doing vector operations. And next, Matplotlib for plotting the values, and scikit-learn for loading our linear regression model. So we're gonna import it. It takes some time for initializing and connecting to the Google server, but we can wait for that. It doesn't, yeah, finish it. So it is connected to the Google server and now loaded those kind of libraries of Python. So as you can see in the table, these were the like data plots or data points I used for plotting the scatter plot. There's 20 values for each height and weight, and we're gonna load that as a height and weight at here. So what this basically do is making a matrix. So in this case, there will be 1 row and 20 column matrix for height and both weight. So let's see like how it looks like. Okay, so this kind of looks like our scatter plot we saw in the slide, right? And yeah, this have a positive correlation, and this have a, yes, it looks like, but without the regression line we had. So we're gonna use the linear regression model here, which we loaded from the model, the scikit-learn. But one caution, one thing you need to like modify at here is the x value. For us, it'll be height. Our independent variable should be in the 2-dimensional array. So basically not 1 row and 20 column, but 1 column and 20 rows. So we're gonna do that by running this code. Okay, then everything is ready. We can make a model of linear regression by using fit function. And we're gonna do that right now. And then it is done. Like we finish it gradient descent, and we now have our linear regression model. Okay, then you can check the result by using some functions or variables at here. So model score. If we run this, then this will gonna give us a value of 0.647, like near that. So what is it? What does it mean? It is a R-squared value. For those who know statistics, R-squared value is the is the validity of the function or model. So we can interpret it as a 76.47% of the test data could be explained by this model. Okay, then let's go next. This is .predict. So it is obvious that what this is going to do. This is going to predict the y value based on given x value using our model. So as you can see, the 103, if we put 103 centimeters as an input, then this returns 87.52 kilograms as an output. So what it is saying is that for our optimized model, for our optimized y equals mx plus b graph, for 183 of height, it is most likely to have 87.523 of kilograms. And then we can get a theta null and theta 1 by running coef and intercept. So basically that is what it is just literally saying it is a coefficient and it is intercept. So we got a theta null and theta 1 value. So basically, as you can see, like in the slide, our theta null and theta 1 was 1.068 and negative 107.9844. And now let's just display it. Let's see how it looks like. And this. So this is how we do the linear regression model process with the scatter plot and the data. Here we go back. And then that was all. Thank you for listening.